Good morning. Welcome to Krishna's classroom. Now we start with the fourth episode of this series. We were exploring the paths from Riemann integration to Lebesgue-Lebesgue. Now we have considerably advanced, but maybe I do a lot of repetition for obvious reasons. But that may be that I believe will be good. And let us see where we stand at the moment. So what we have done is this: is we found that while going from Riemann integration to Lebesgue integration, we have to introduce the concept of length for a larger class of sets than intervals. The concept of length for a bigger class of subsets of we did this in two stages. We did this in two stages. The first one was define outer measure M star for all subsets of okay. So we worked on PR. And M star had the property that for intervals it coincided its conventional length. Okay. Now the second problem that we encountered was, because I didn't prove it or anything, M star failed to meet the desirable countable additivity for fail to meet the desirable countable additivity. It is defined for all subsets. There is no problem with it. Okay. But now, having come to a situation of this kind, we defined what are the measurables. Now let me just recall. E is measurable. If measure of A, m star of A, okay, m star of A intersection of E complement. This schematically is in Venn diagram. This is E. So this is an arbitrary A. Has been cut into two parts. One is this, the other one is this. So this is A intersection E. This portion is complement. What we said is something simple. M star of A, which is defined, M star of A intersection E is defined, M star of A intersection E complement is also defined. What we want is the outer measure of these two portions should add up to give you the outer measure of A. Okay. Now this is not easy to explore this in the case of subsets of the real line. Okay. So I am not going to do that here because it is more sophisticated. Whereas once we introduce the concept of general measure, which we are going to, that is our objective, we will construct some nice examples to give an insight into what this is. Now, it simply says the following. I mean, at least in a layman's understanding, what it says is E is a nicely cutting set, in the sense that it cuts any subset into two portions whose outer measures would add up to give the outer measure of the whole set. If E is such a set, we call that the measure of the set. So that is clear. That's what we did last night. And then we could show that this is sufficiently large. Such a collection is sufficiently large. To include the empty set, the whole set, all open sets, all closed sets, all intervals, and the so-called countable countable union and countable intersection of such sets. Countable union and countable intersection of such sets. Now that means the class of measurable sets is indeed extremely large. Of such sets. Therefore, it includes not only open sets and closed sets, but also sets, many sets which do not belong to this type. Okay. So it's huge enough probably to serve our purpose. Okay, but it's indeed not, entire class of and there is a very famous theorem which says that there exists a subset of R which is not measurable. It's not measurable. That means it does not satisfy this condition. Especially go to the construction of that's simple. That's worthwhile in your strive to do mathematics. Okay, so we have got now a class and we designated it script A, which is a sigma algebra of Sigma algebra means the empty set belongs to that, the whole set belongs to that. If A belongs to that, A complement belongs to that. If the countable union of measurable sets is again measurable, countable intersection of measurable sets is measurable. And furthermore, one more thing is true, because, okay, and we defined a measure, the Lebesgue measure. By measure of for every E belonging to connections. So from outer measure, you were willing to sacrifice certain things like properties like countable adequacy, sacrifice certain sets for the sake of getting some nice properties valid. And we also define E, the translate E in R. That is E belonging to and we found E the translate also belongs to that, and we also have M of E equal to, or M is translation. Oh, this is not it. So that is the current position. Okay. So now everything is ready. So the Lebesgue measurable space is now ready. So R with the subcollection of sets A with with now some of the interesting observations are, if A is, if one need, and now of course you should not forget the fact that extended real valued function, in fact more precisely non-negative function, on if necessary we enlarge this class slightly by, we also, okay, so we have what you call the sets of measures. Now one of the things that you have is that empty set is equal to, now second property is that now for any countable collection of measurable sets En with measure of equal to 0 for every n, measure of this is also equal to 0. In fact, what we have is, in general, we have, this is what I said, countable additivity, measure of is equal to so that proves it. That is what you call countability. These are some of the important things, and you can, and you also have if A and B are measurable. Okay. Yeah, let me make a remark here. However, a measurable set with measure 0 may not be countable. It may not be a countable set. So we said that. Okay. That follows from here, because you see, all singletons are countable. Therefore, any countable set, any countable collection is, because you see that this one. Is a union of that. Okay. Now, what we could assert is that the measure of this is 0. But the natural question that you ask at this stage is suppose you have a set with a measure 0. Can you say it is countable? The answer is no. Why? Consider the Cantor set. Go through the construction of the Cantor set. I am not going to spend time on it. Okay. Cantor set. It is a zero one, but however, it is not countable. So there are sets which are not countable having its measure equal to 0. So just from the statement that the Lebesgue measure of a set is 0 does not imply it is countable. That's what I meant. And also one more thing that you can say is that if E is measurable, you cannot say that any subset of E is measurable. So caution. Does not imply all subsets of E are measurable. subsets of one example is, of course, the whole of R is measurable, but the subset that we have considered which is not measurable is a subset of this, which is not measurable. I mean, so there exists subsets of R which are not measurable. So that is clear. So you cannot in general say that P is a measurable set. So we do a sort of completion of measure by imposing the condition. All subsets of a set of measures U are measurable with this, of course, enlarges the sigma algebra. Okay, so that's a condition. So we slightly enhance the class of this. So if this is not true, we already add these things and or include these sets also into this. That is, you take all sets of measure 0, then put in all subsets of such sets, and then if you want, you enhance the class of class B. So we assume that this is already taken care of. Okay, and we use the same. So our groundwork is now complete. Okay, now we are in a position to take up integration theory. I mean, there are lot of questions comes. You take a what you call a monotone sequence of measurable sets, the union measurable, etc., etc. Such questions are asked. Okay, so they are all discussed in detail in NIM. Now, I think I don't want to spend time on that, but we are now in a position to define what is measurability. Because after all, our interest is to consider functions defined on R or subsets. So let us let F be a R into that is f is an extended real value function. That means it may take values plus infinity or minus infinity at some places. Okay, so we are not going to exclude that. That is what you call an extended real value. That is f is by which you mean it may take plus infinity, the values plus infinity or minus infinity at certain points on. Now we also consider, so if E is a measurable set, then we also consider extended real value functions on. Okay. Now, since we are working on extended real value functions, we may have to take the sum of these functions, product of these functions, and so on. Okay. Meaningfully, you will have to take. So we'll have to make some conventions. Okay. So let us denote stop. So on R star, that is this, we set the following characters. Two for computations. This is an extension of addition and multiplication. Addition and multiplication on R to R star. So we do this as this. We write x plus infinity equal to infinity. Minus. Then we have plus infinity It's not. We don't need that. And that's one problem. So this is not defined. Now we define 0 into infinity equal to 0. Addition and multiplication are commutative. So the extended addition and multiplication are commutative on R star. Okay. Now these are required. These conventions are required when we introduce integration theory. Okay. Now the reason why we do this. See, suppose you have an infinite rectangle. Yeah. This is the situation. You have an infinite rectangle. And suppose, what would you take as the area enclosed by this line? Okay. This is possibly of course, for any rectangle, we define the area as this A. This is the area is, suppose this is the R, then area of R, or what you call AB. This is what we postulate. I mean, this is the usual concept of area, and in terms of the areas of rectangles, we approximate the area of a or the integral of a function. But now suppose you have the set A cross R star, or even this. Infinity included. Now you see the length of this is infinity and the measure of this is 0. Therefore, this is measure of which is equal to 0 times infinity. And this is actually a line. This is actually a line. What is the area enclosed by the set, the set of points in a line in R2? It has to be, this area has to be, so area of this set. So area of this has to be equal to 0, and this has measure 0, and this is equal to measure of into this is equal to, and this, because it's a line that you are considering, this has to be 0. This is the area. So this is equal to this one, and that has to be 0. So you need a calculus where of the extended real line to follow the following multiplication rule, namely 0 into infinity is 0. The other one is plus infinity plus minus infinity need not be finite. I mean, you don't know. Okay, so we write plus infinity minus infinity is not, plus minus infinity is not defined. Okay, so these are the two things. With the caution, we extend the addition and multiplication on stuff. Having done that, now we talk about measurable functions. We'll define them. A measurable function on E where E is an element of script is said to vanish so we first define what is measurability. Okay, so I'm not. Let me define. So okay. An extended immeasurable is defined as said to be measurable is said to be measurable, or what you call so we are using Lebesgue measurable sets. Is said to be measurable if for each C belonging to R now there are several equivalent forms. I will just list out the equivalent forms. The equivalent forms are the equivalent conditions are C belonging to R. Third condition is fourth condition is that means 1 if and only if, 2 if and only if, 3 if and only if, 4. So they are all equivalent conditions. Okay. What do we mean by a set is measurable? A set is measurable means that set belongs to the sigma algebra. Okay. That is it is an element of in this case A. In general, I mean whatever be the measurable class of sets that you choose for your purpose. will be made use of. Okay, so this is what we mean by that. Now you can show that this is measurable, F measurable. So all measurable. No, what I mean to say is all constant functions. Okay, we are now talking about functions. So we have all constant functions are now you see it's equally true that if F is measurable, F inverse of an open set is measurable. Is measurable. That means belongs to A. Okay. Now why do we need this? Let us go back to our strategy for integration. So we have changed our strategy now, and we try to catch hold of more functions integrable by changing our strategy of integration. In the case of Riemann integration, we subdivided the domain into intervals. So we had a partition of the domain. But now what we do is we start with partitioning the range to a union of disjoint intervals. And what you get, if you look at the problem, it is this. Okay. So what is F inverse of, suppose this interval is CD. So this is the set F inverse of CD. Okay. So it is this. CD. This is F inverse of CD. And whenever we want this to be measurable, so we want so that measure of is defined. Now you try to see an approximation for this. See this portion So suppose you take f restricted to f restricted to f. Okay. Now what is the integral of g? The integral of g is the area enclosed over here. Okay. Now what we want is we do two approximations. One is this, the lower approximation. The other one is the upper approximation. Upper approximation I mark with a different color. So you see that this integral g should be squeezed between, what is that? The area, the rectangle marked, and the rectangle marked with the color. Okay, right? So this is our perception. But what does this need? This needs, this is actually equal to the height c into measure of what? F inverse of less than or equal to integral of g less than or equal to t into measure of f inverse of CD. This is what you get. Okay. So these sets have to be, so if you want to integrate, we want these sets to be in script A. Okay. So to define integration through our strategy, so measure of make sense. This happens when the set F inverse of A measure. Or we can define an integral only when F is a measurable function. So this is the important part. Okay, that's why we talk about measurable functions. If that is not, suppose this set is not measurable, what will happen? How do you write a measure for that? Suppose this is a non-measurable set, then it is not measurable, then there is a problem. Therefore, once f is measurable, then the pullback of every interval, the pullback of every interval is a measurable set. Okay, right? So f is measurable pullback or even CD is so that measure of that is the important. So that's the concept of a measurable function. Okay. Now, do we have a huge class of functions? First of all, you observe that all constant functions are measurable. Okay. Secondly, all functions which take finitely many values are measurable. All constant functions. To all finite or countable are measurable. All functions which take countably many values are measurable. So you see, have a lot of functions which so this is because f is continuous if F inverse of open for every open set R. It's not 0, this is open set. Okay. Now all open sets are measurable. Which implies F inverse of O measurable. Which implies F so all continuous functions are measurable. So you have a large class of functions now which are measurable. Already the class is large. Okay. Even if they have some discontinuities, they also will be measurable. In fact, you can show that all Riemann integrable functions are measurable. That's huge. So the collection of functions which are measurable are huge. And what we try to do is to define an integral for measurable functions. I think that's a nice place where we stop for the time being, and then we now explore how to define integration, okay, which is done in several stages. First of all, we take what are called bounded measurable functions defined on sets with finite measure. Okay. There we use the same strategy as you did in the case of Riemann integration. Then we approximate more general functions using these functions. Okay, and then use the limiting process to define integral of a far more general functions. And eventually, in stages, we arrive at the integral of a sensible definition of the integral of every of a Lebesgue measurable function. Okay, so let us do that. That will be our task. So I think I will stop here and then take it up in my next lecture, maybe day after. Okay. So thank you very much. Have a nice day.